Okay, let's talk about chapter 2. First, let's talk about scientific notation. Scientific notation helps us look at numbers that are either really big or really small. A number in scientific notation has two parts, a coefficient or a decimal part and a power of 10. So for example, if we look at 2,400, in scientific notation, we have a coefficient or a decimal part of 2.4, and we have a power of 10 to the third power. So we want our coefficient to always be between 1 and 10, or 1 and 9, So in order to do that, we take our original number and we move the decimal either to the right or to the left until we get a coefficient between 1 and 9. So let's look at these examples. So we have 5,983. In scientific notation, that's 5.983 times 10 to the third. In order to get the 5.983, we had to move the decimal place to the left 3 times. So that's how we get the power of 10 to the third. The bottom example, we have 0.00034. And in scientific notation, that's 3.4 times 10 to the negative fourth. In order to get that coefficient of 3.4, we had to move the decimal to the right 4 times. So that's how we get the power of 10 to the negative 4. So if we go to the left, we have a positive power of 10. If we go to the right, we have a negative power of 10. So here's some examples. 0.0000674 in scientific notation is 6.74 times 10 to the negative fifth. In order to get a coefficient of 6.74, I had to move the decimal to the right 5 times. That's how I get 10 to the negative 5. In the next example, we have 38 with 10 zeros. So that's 3.8 times 10 to the 11th. In order to get a coefficient of 3.8, I had to move the decimal place to the left 11 times. In the next example, we have 0.0239. In scientific notation, that's 2.39 times 10 to the negative 2. In order to get a coefficient of 2.39, I had to move the decimal to the right 2 times. That's how I get 10 to the negative 2. Then in the final example, we have 4,561,000. In scientific notation, that's 4.561 times 10 to the 6th. In order to get the coefficient of 4.561, I had to move the decimal place 6 times to the left. That's how I get 10 to the 6th. Okay, let's talk about measured numbers. Every measured number has a certain and an estimated or uncertain part. So the estimated number will always be the last digit in your measured number. Everything else you know for certain. So let's look at these rulers. So I'm measuring this piece of wood. In the first example, I can see that for sure it's at least 4 centimeters. But it's between 4 and 5, but there's no tick marks between 4 and 5. So all I can say for sure is 4 centimeters. So I need to guess 1 digit past that. So I would say this is 4.5 centimeters. That 0.5 is estimated. The 4 I know for sure. In the next example, we have the same piece of wood. We have a better ruler. Now we have 10 tick marks between 4 and 5. So I can see for sure that it's 4.5 centimeters, but it's somewhere between the 0.5 and the 0.6. So I might guess that this is 4.55 centimeters. That last 5 is estimated, but I know the 4.5 for sure. Then in the following example, we have a new piece of wood, and we can see that it's 3 centimeters. I know that for sure. Even though it looks like it's right on the 3, I still have to guess 1 digit past that. So I would say this is 3.0 centimeters. That shows you that you knew the 3 for sure, but you had to guess the 0.0. Okay, let's look at this example. So for this coin, I can see for sure that it's 24 millimeters, but it's somewhere between the 4 and the 5 millimeter mark. So I have to guess that last digit. So I would say this is about 24.6 millimeters. That 0.6 is estimated, the 24 is certain. Okay, so let's talk about significant figures now. all the digits, including the estimated digits in a measured number. So here are the rules. A number is a significant figure if it's not a zero. So any non-zero digit is significant. So in this measured number 4.5 grams, we have two significant figures. 122.35 meters, we have 5 significant figures. The next rule is a zero between non-zero digits, or a sandwich zero, will be significant. So in 205 degrees Celsius, we have 3 significant figures. We have the 2 non-zero digits, and then the 1 sandwich zero. In 5.008 kilograms, we have 4 significant figures, the 2 non-zero digits and the 2 sandwich zeros. Our next rule is a number is significant if it's a zero at the end of a decimal number. So 50 liters is 2 significant figures, the non-zero digit and then the zero significant because it's at the end of a decimal number. If it was just 50 without that decimal point, we'd only have 1 significant figure. In the next example, 16.00 milliliters, we have 4 significant figures. The 1 and the 6, the 2 non-zero digits, and those 2 zeros are significant because they're at the end of a decimal number. They're after a decimal place. The final rule for significant numbers is that a number is significant if it's in the coefficient of a number written in scientific notation. So 4.8 times 10 to the 5th meters, our coefficient has 2 digits, it's 2 significant figures. 5.70 times 10 to the negative 3rd grams, 3 significant figures. Our coefficient is 5.70, there's 3 digits, 3 significant figures. So as you can see, scientific notation isn't just helpful for looking at numbers that are really big or really small, it also really shows you what your significant figures are. Okay, and let's look at the rules for a zero not being significant. So 0 is not significant if it's at the beginning of a decimal number. So for example, 0.0004 seconds. The only significant digit is 4, so this has 1 significant figure. All of those zeros are just placeholders. The next example, 0.075 centimeters. The only significant digits are the 7 and the 5, so we have 2 significant figures. Again, those zeros are at the beginning of a decimal number, and they're just placeholders. And the next rule is a 0 is not significant if it's used as a placeholder in a large number without a decimal point. So 850,000 meters, we have 2 significant figures, the 8 and the 5. All those zeros are just placeholders. 1,250,000 grams, we have 3 significant figures, the 1, the 2, and the 5. Again, all of those zeros at the end are insignificant. They're just placeholders. Let's look at some examples. So 0.0035. We have 2 significant figures, the 3 and the 5. The zeros are insignificant because they're at the beginning of a decimal number. They are just placeholders. 1.080. We have 4 significant figures, the 2 non-zero digits. Then the 0 between the 1 and 8 is significant because it's a sandwich 0. The 0 at the end is significant because it is after a decimal point. 2,371, we have 4 significant figures, all non-zero digits. 2.97 times 10 to the 5th, we have 3 significant figures. There are 3 digits in the coefficient of the scientific notation number. 100.00, we have 5 significant figures. The 1 is significant, and then all the zeros are significant because they're at the end of a decimal number. 100,000, just 1 significant figure. There's no decimal. All of those zeros are placeholders. Okay, let's talk about exact numbers. Exact numbers are numbers obtained by counting items or using a definition that compares 2 units of the same measuring system. So for example, for counted items, I have 8 donuts, 2 baseballs, 5 capsules. I just counted the number of donuts, baseballs, and capsules I had. And then define equalities. So within the metric system, 1 liter equals 1,000 milliliters. 1 meter equals 100 centimeters. A kilogram equals 1,000 grams. In the US system, 1 foot equals 12 inches. 1 quart is 4 cups. 1 pound is 16 ounces. These are just defined equalities. They're exact numbers. We did not take a measurement to get these numbers. These do not count towards significant figures when you're doing a calculation. So let's talk about sig figs and calculations. The first thing I want to talk about is rounding off. So if you're rounding a number and the first digit to be dropped is 4 or less, then it and all the following digits are to be dropped. So we have 8.4252. I want to round it to 2 significant figures. So I have 8.4. The number after the 4 is less than 4, so I drop it and everything following it. And then if the first number to be dropped is 5 or greater, then the last retained digit is increased by 1. So here I have 8.4252. So I want 3 digits. So I have the 8.42, but the number after the 2, the first number to be dropped is 5. So I have to increase that 2 by 1. So I get 8.43. Okay, here are the rules for multiplication and division. So in multiplication and division, the final answer is given the same number of significant figures as the measurement with the fewest sig figs. So let's look at this example. 2.075. That's 4 significant figures. The 3 non-zero digits, and that 0 is significant because it's sandwiched. 0.585 is 3 significant figures. That 0 is not significant because it's at the beginning of a decimal place. It's just a placeholder. 8.42 has 3 significant figures, all non-zero digits. 0.0245 has 3 significant figures. Those zeros are insignificant because they're at the beginning of a decimal number. So we are multiplying and dividing one number with 4 sig figs and 3 with 3 sig figs. So our measurement with the fewest number of sig figs is 3 sig figs, so our answer should have 3 sig figs. Let's do some examples. So here we have 1.01 times 0.12 times 53.51 divided by 96. So 1.01 has 3 significant figures, 0.12 has 2, 53.51 has 4, and 96 has 2. So our measurement with the least number of significant figures is 2. So our answer should have 2 sig figs. So here we get this answer. To round it to 2 sig figs, we get 0.068. Let's look at another example. 56.55 times 0.920 divided by 34.2585. 56.55 has 4 significant figures. 0.920 has 3. That 0 at the end is significant because it's the 0 at the end of a decimal number. The first 0 is not significant because it's a placeholder. It's a 0 at the beginning of a decimal number. And then 34.2585 has 6 significant figures. So our measurement with the least number of significant figures is 3. So our answer should have 3 significant figures. So we'll round this to 3 significant figures and we get 1.52. Okay, let's talk about addition and subtraction. The final answer is written so that it has the same number of decimal places as the measurement with the fewest number of decimal places. So 104.45 has 2 decimal places, 0.838 has 3, and 46 has none. So our answer should have no decimal places. Let's look at this example. 0.978 plus 125.1 minus 1.22. So 0.978 has 3 decimal places, 125.1 has 1, and 1.22 has 1. So our answer should be rounded to have 1 decimal place. Let's look at one more example. 0.765 minus 3.449 minus 5.98. 0.765 has 3 decimal places. 3.449 also has 3 decimal places. But 5.98 has 2, so our answer should have 2 decimal places. So we get negative 8.664. Again, we want 2 decimal places, so we get negative 8.66. Okay, let's talk about if you have multiplication and division within the same problem. How do we get sig figs? So in this example, we have 6.78 times 5.903 times, and then in parentheses, 5.489 minus 5.01. So what you'll do first is you'll do the number, or you'll do the calculation within the parentheses. So that's the 5.489 minus 5.01. We get 0.479. So if you look at the third row here, what we end up with is 6.78 times 5.903 times 0.479. The 7 is underlined because that is where we'll round for significant figures. When we did that subtraction, our answer should have 2 decimal places because our 5.01 has 2 decimal places, whereas 5.489 has 3. But what we want to do in a calculation is we want to keep one digit after the significant figure. But we'll underline where our significant figures end. So then we can multiply these numbers. We get 19.1707. Our answer should have 2 significant figures. Because we're doing multiplication and division, our answer should have the number of significant figures as our measured number with the fewest number of sig figs. So this number has 3 sig figs, this has 4, this has 2, so our answer should have 2. Let's look at another one. So again, first thing we'll do is the calculation in parentheses. So this is this multiplication calculation. So 5.4 times 0.916, and we get 4.9464. This should have 2 significant figures because our number with the fewest number of significant figures has 2. So in this row you can see we underline where our significant figure should end. Then we can do the subtraction. Remember, the rule for subtraction is that our answer should have the number of decimal places as our measured number with the least number of decimal places. Here we have 3 decimal places, here we have 1. So our answer should have 1 decimal place, 14.7. Okay, now let's talk about prefixes. So prefixes are just, we put them in front of a unit to either increase the size of a unit or decrease the size of a unit. So for example, tera is 10 to the 12th. So 1 terasecond equals 1 times 10 to the 12 seconds. Or a kilo. A kilo is 1,000 or 10 to the third. So 1 kilometer is 1 times 10 to the third meters. Then prefixes can also decrease the size of the unit. So for example, deci, little d, is 0.1 or 10 to the negative 1. So 1 deciliter equals 1 times 10 to the negative 1 liters. Or centi is 10 to the negative 2. So 1 centimeter equals 1 times 10 to the negative 2 meters. And just to point out, in medicine, micro, this is the Greek number mu. Oftentimes in medicine, it'll be abbreviated to MC because the symbol mu can be easily misread. It can often look like an M, which could be milli. So instead of saying 1 mu g, it might be written as 1 mcg. So you'll see both sometimes. So here's some common prefixes: kilo, centi, milli, micro, nano, and pico. These are ones that I would tell you that you should learn. Okay, common equalities here. So here's equalities within the metric, within US, and metric to US. Numbers in any equality between 2 metric or 2 US system units are definitions. They're exact numbers, so they do not count towards significant figures. But when there's an equality between a metric and a US unit, one number is obtained by measurement, so it does count towards significant figures. So for example, 1 liter is 1.06 quarts. This 1.06 is a measured number. So if we're doing a calculation using this equality, this 1.06 will count towards significant figures. Okay, so let's look at a practice problem. So we want to convert 164 pounds to kilograms. So first let's come up with a plan. So we're going to need to start with pounds, we need some US to metric factor, and we're going to end in kilograms. So let's state the equalities. So we know 1 kilogram equals 2.20 pounds. So let's set up the problem to cancel units and calculate the answer. So we're given 164 pounds, and then we have our conversion factor of 1 kilogram over 2.20 pounds. We get an answer of 74.5 kilograms. So we always start with the given number, then our conversion factor, and the unit for the answer should be on top, and then we'll get our answer. Okay, let's look at another problem. So Greg's been diagnosed with diminished thyroid function. His doctor prescribes a dosage of 0.150 milligrams of Synthroid to be taken once a day. If the tablet in stock contains 75 micrograms of Synthroid, how many tablets are required to provide this prescribed medication? So again, let's start with the plan. So we need to go from milligrams to micrograms with some metric factor, then from micrograms to number of tablets with some clinical factor. So to state the equalities, 1 milligram is 1,000 micrograms, and 1 tablet is 75 micrograms. Okay, so then we're going to set up the problem to cancel units and calculate the answer. So we start with what we know, which is 0.150 milligrams of Synthroid. Then we want to get to micrograms, so that will be on top. So we have 1,000 micrograms over 1 milligram. And then here we want tablets. So we have tablets on top and then micrograms of Synthroid on bottom. Make sure our units cancel. Milligrams, milligrams, micrograms, micrograms. So we end up with an answer of 2 tablets. Okay, let's look at another problem. The Toyota Prius has an EPA estimated city gas mileage of 48.0 miles per gallon. What is it in kilometers per liter? So we know that 1 mile is 1.609 kilometers and a gallon is 3.785 liters. So somehow we want to go from miles per gallon to kilometers per gallon to kilometers per liter. Okay, so here we go. So we know 48.0 miles per gallon. So we know 1 mile is 1.609 kilometers. We want kilometers, so that's going on top. And then we know 3.75 liters is 1 gallon. The gallon goes on top this time because we want it to cancel with this gallons on the bottom. And in our answer, we want our units to be kilometers per liter, so we want liters in the bottom in our answer. Just make sure our units cancel. So miles cancels with miles, gallons cancels with gallons, so we're left with kilometers per liter. What about when you have units raised to a power? So when you're converting quantities with units raised to a power, such as cubic centimeters, you must also raise the conversion factor to that power. So let's look at an example. So we want to convert 1,255 centimeters cubed to cubic inches. So we know that 2.54 centimeters is equal to 1 inch. So to get cubic centimeters, we need to cube both the 2.54 and the centimeters. We also need to cube the inches. So what we get is 2.54 cubed, centimeters cubed equals 1 cubed, inches cubed. So we end up with 16.387 centimeters cubed is 1 inch cubed. So now we can do the problem. So we start with what we have, 1,255 centimeters cubed. We want inches cubed, so that goes on top. And then on the bottom, we have 16.387 centimeters cubed. Make sure our units cancel, and they do. Our centimeters cubed both cancel, and we end up with 76.59 inches cubed. Okay, let's just briefly talk about density. So density is the comparison of the mass of an object to its volume. So density equals mass over volume. Every substance has a unique density. Usually we express densities in either gram per centimeters cubed or grams per milliliter. Let's do a problem here. So let's determine the density for a 0.215 milliliter sample of solution that has a mass of 0.258 grams. So we want grams per milliliter, mass over volume. So density equals 0.258 grams divided by 0.215 milliliters. So that we get 1.20 grams per milliliter.